Okay, question 8. We've got an athlete is using a fitness device. It's some sort of springy thing here. They stretch the spring by pulling the handles apart. We've got the spring constant, so remember that's K. And I'm just going to get any formulas I might need. So that's Kentucky Fried X-rays. I also might need the elastic potential energy equals half kx squared. They've got some work here and a time. So work and energy are both measured in joules. So it looks like I might need my PET formula, energy, time. And now let's go through. Which of these bits do I need? Calculate the useful power output of the athlete when stretching the spring. So now we know I'm going to need this, my PET formula. Now let's just go in. You're in joules, I'm happy with that. You're in seconds, I'm happy with that. Oh, that's nice and easy. So P equals E divided by T. 45 divided by 0.6 equals 75 watts. 2 marks. On to the next part. I'm guessing we're going to be messing with that spring now. So calculate the extension of the spring, and we've got the energy. So clearly the work that they've done is the energy that they've put into this spring. So I'm going to need my EPE equals half kx squared, and it wants the extension, so I want to get x on its own. So go through the process. To get rid of the half, times both sides by 2. So you're gone, and that's 2 EPE, or 2 lots of the work, because the work is the elastic potential energy. I'll tidy that up. That's really rubbish. In fact, let's do this. Sorry, guys. So EPE equals half kx squared, and you get that in your formula sheet. And we've just said, well, first job, times both sides by 2 to get rid of the half. So EPE equals kx squared. I want to get x on its own. Whoops. I want to get x on its own. So divide both sides by k. So 2 EPE over k equals x squared. And I do not want x squared. I want x. So square root both sides. And I'm left with x equals the square root of 2 lots of the elastic potential energy divided by the spring constant k. Let's check they're in the right unit. Yep, newtons per meter is the unit I want. So that's kind of nice, but lovely rearrangement. So we know EP equals half kx squared. Rearrange it like I did there to get x equals 2 lots of k, the EPE, sorry, that should be EPE over k. I could put k in there because actually it's the energy that I put in moving the spring. So 2 lots of 45, 2 lots of the work, divided by 140 comes to 0.801, and I could just write that in. I'm going to go 0.8 meters. Job done. Next one, the student investigates stretching a long piece of rubber. Here we go. So there's the rubber. I've got a pulley. We're going to dangle some weights on. When I add the weights, this piece of rubber is going to get stretched and go a little bit lower. So you can imagine, hang another weight on there, and this will end up going a little bit lower. So there we go. There's my extra weight. Okay, they put just enough weight to make the pivot just tight. So they want to plot a graph to show how the extension varies with the force. So we're just going to hang more and more weights. Describe how they could measure the extension. Oh, okay. So what I'll do it visually first, and then so what I could do is put a mark on the rubber there. Maybe get a clamp stand and just put a marker. And then the crucial part is hang on your new weight. My marker will now need moving down, and if I mark out that, so if I do start and end, that's my extension. It's just asking me how do I do it. So in terms of words, add a mark to a fixed point on the rubber and use a ruler, and because it says describe how to do it, so I need a ruler, so that a ruler is going to go here, measure the new additional length, and the next part is my extension is the length at the end minus the length at the start. Done. Okay. The student retains a series of force and extension. So we've looked at this with Hooke's law. We've got extension in meters and force in newtons. And if it was obeying Hooke's law, we know it'd be straight line, it'd be directly proportional. Clearly, this is not obeying Hooke's law because I've got curves. The next part is it's telling me, well, I get this set of results when I load it. And then when I unload it, so when I take the load back off, I get this set. This part here, that's the heat energy that I put into stretching the rubber band. Thank God they're not asking you to calculate it. Here we go. So explain how the shape of this graph shows it's different from the spring. So a spring would obey Hooke's law until we get to the elastic limit, and then it'll curve up. This clearly is behaving differently to the spring because it's curved all over the place, and there's a difference between the loading and unloading. So the graph shows a non-linear relationship for the band. The spring would show direct proportionality. And here, if I was doing it with a spring, as I loaded it, I'd get that, straight line. And then as I unloaded it, I'd get the same results, give or take. Assuming I've not got... Here, we've got a difference for this rubber band. So the points for loading do not match the points for unloading. Tricky question, actually, that. Next one, the area between the curve and the extension responds to the work done, suggests what the shaded area of the graph represents. So the elastic potential energy of the work done in loading and unloading the band. So it's the difference between the loading and the unloading. That's the elastic potential energy stored in there. It's also the, so that's what, sorry. If I just had a straight line like that, this area under here, that's the elastic potential energy, half kx squared. What this is asking is, what's all this stuff in here? That's the thermal energy that's been lost in stretching the rubber band. So the shaded area shows the heat energy lost into the surroundings from the band. That's that one done. Tricky question, that.